we'll cover correlation and linear regression, particularly how to describe the relationship between two quantitative variables. So specifically, we'll cover the scatter plots, what correlation is, we'll move into simple linear regression, talk about things like R-squared and linearity and nonlinearity, and then we'll talk about writing good conclusions and using good graph techniques. Now, there's a lot of moving parts in correlation and regression, so to help some of the things stick a little bit more, we're going to work through the same example throughout the entire unit, and the example is this. We are part of an analytics group that works for a business, and this business is particularly interested in selling something. And the way they're going to increase sales is to advertise on YouTube. Now, they've got two simple questions for us. Number one, based on previous budgets and sales, do you think advertising on YouTube is worth it? And question number two, how many units do you think they could expect to sell if they spent $200,000 on YouTube advertising? So they give us the graph of the data that they said they have. They've got the YouTube advertising in thousands of dollars and the sales in thousands of units. So this is a graph of all those different data points. So each point here represents the amount they spent on advertising and then the sales corresponding to that. And although that we could definitely see an upward and to the right direction, like the more you spend, the more you sell, which would kind of make intuitive sense, we want to get into the nitty gritty. Like, what is the difference between spending $100,000 and $200,000? And can we predict or estimate how much you'd be able to sell in each of those scenarios? Now, the graph I just had up is called a scatter plot. It's usually the way we describe two quantitative variables. It provides a case-by-case view for those two variables. That is, every dot on the graph corresponds to two numbers, one on the x-axis and one on the y-axis. A variable is on each one of the axes. So to know what the values of those variables were for that observation, you simply trace back down or across to the axis and read off the value. So in this particular scatter plot, I'm showing some home prices and incomes for particular families, and I've got one of the observations circled in red. That observation corresponds to a household price of just under $140,000 and an income just under $80,000. Now, we use a scatter plot for the same reason we use any of our other graphs. It's an effective way to look at trends and patterns between these two variables that you wouldn't be able to otherwise see if you just had like a spreadsheet of these two variables. Here's a zoomed in version of the scatter plot for the YouTube and the sales data. So on the right, I have what you would see in a spreadsheet, and on the middle or towards left, I've got the scatter plot. So that green dot that I have on the bottom, that's associated with row number one, where the amount spent on YouTube advertising is $239,000 and the sales is 12,720 units. This blue dot corresponds to row 1, 2, 3, 4, 5. So that corresponds to when YouTube sales was $117,000 and the sales was 11,640 units. And then last but not least, the red dot way in the upper right corresponds to one of the lower rows, where the amount spent on YouTube advertising was $337,000 and the corresponding sales was 29,000 units. Now that's true for any one of these dots. The yellow one here also corresponds to an amount spent on advertising and a corresponding amount of sales. To figure both of those out, you can just retract back to the x-axis and the y-axis. That corresponds to what seems to be about $150,000 on YouTube advertising, and what looks to be about 17,500 units sold. Other than just describing the observations, there's usually three components to a scatter plot that we like to describe. The three components are form, direction, and strength. So let's walk through those real quick and then we'll do some examples. The only thing that we're going to mention in terms of form is whether the data is linear or not. So when I say the word linear, what I mean is that the dots form a relative straight line, or if you want to think about them as a swarm or cloud of points, that they stretch out in a consistent general straight form. Whether it goes up or down doesn't matter, just whether it's straight or not. If it is straight, we call that linear. Now there's a lot of other shapes you could see. So these two scatter plots on the right, one of them kind of looks like an upside down parabola. The one on the right hand side looks like it kind of curves up and to the right. Those are different shapes, but for us, all it matters is whether it's linear or not. So since these are not, we are going to refer to them as non-linear. Now when we call a scatter plot linear or non-linear, What we're describing is the rate of change between data points and whether that rate of change is consistent or not. So here's a set of data. This is the size of diamonds in carats opposed to their price. Now, if I take a diamond that is half of a carat and then another diamond that is 1 carat, the price difference is about $2,500. So $2,500 for the half a carat and $5,000 for the 1 carat. So that's where the $2,500 difference would come from. But if I was to consider 2 other diamonds, 1 carat and 1.5 carat, their price difference is $5,000, even though the difference in size is the same. It's still a half of a carat difference. The difference in price is much more now. That rate of change, that price difference, is not consistent for the same size difference. That is what we mean by non-linear. And that's what causes the scatter plot to not be linear. In other words, have gentle curvature to it, when the rate of change between the data points is not constant. On the other hand, this is a scatter plot of temperature in degrees Fahrenheit and the associated sales in heating. So I picked 2 temperatures here, 20 degrees and 40 degrees, and their associated heating sales was 4,000 and 3,000. That is a difference of $1,000. Now I've picked 2 more temperatures, 40 and 60. They also have a difference of 20 degrees, but if you see their price difference is also $1,000, 3,000 to 2,000. So here the price difference is constant for the same difference in size. And it's exactly this, when the rate of change is constant, that creates that linear shape, that straight line. In this case, a straight downward line. Now for us, describing this is a clear eyeball test. We're not calculating anything per se, even though we could. We're just going to look at it and say, to the best of our ability, does this plot generally follow the shape of a straight line? If so, this is linear. If it does not, and it has some other general shape like a curvature or an S shape or whatever, we're going to call it nonlinear. The next characteristic we want to describe is direction. Now, in this particular scatter plot, what we have are the smaller values of x, which are associated with the larger values of y, that is the points on the upper left, and they go from larger values of x down to smaller values of y, the points in the bottom right. In other words, we've got a direction that's going from the upper left to the bottom right, and when we have that direction, we call that negative, or a negative association between these 2 variables, temperature and heating sales. On the other hand, in this scatter plot on the right-hand side, we've got larger values of x associated with larger values of y, so some points up and to the right. Then we have some smaller values of x associated with smaller values of y, so points in the bottom left. So in this particular case, what we have is a direction that's going from the bottom left to the upper right. And when that's the direction we have, we call that positive, or a positive association between these 2 variables. So in short, if you've got a graph that goes down and to the right, we call that negative. If the graph goes up and to the right, we call it positive. The last characteristic, and the trickiest one to describe, is strength. Here what we're trying to do is describe how loosely or tightly scattered the dots are. So in this particular scatter plot, I have people's height in meters and their weight in kilograms. And in this case, you've got dots all over the place. A more technical way to describe that is if you were to focus on any one height, like 1.6 meters, it's very difficult to say what weight that would correspond to, because there are some observations that are as low as 60 kilograms, but some as high as 120 kilograms. So if you told me somebody was 1.6 meters high and you asked me how much do I think they weigh, I would have a very large range of guesses for you, either 60 kilograms or 120 kilograms. And that's not a very good prediction. That is, knowing someone's height here doesn't help me much when predicting the variable y, weight. When that's the case, we call the strength between the 2 variables weak, or that they have a weak association between them. Now, as opposed to the scatter plot here on the right, where I have their weight in kilograms and their waist circumference in meters. Now, if I focus on any one particular weight, say something like 100 kilograms, and you were to ask me what do I think their waist circumference is, I would actually have a pretty tight list of guesses. With this data, I would say that those observations are between somewhere like 1 and 1.2 meters, as opposed to a very wide range that wouldn't be very useful at all. So in this case, we would say knowing one's weight, x, helps when you're trying to predict their waist circumference, y. So it's this case where we would call the strength between these 2 variables strong, or that they have a strong association between them. Now, strength can be tricky because it's all an eyeball test up to this point. So it's a little easier to tell whether something is linear or not. But strength, I mean, very strong, kind of strong. How are you supposed to describe that? So imagine just having a number instead. A number we could just calculate that would tell you the strength of the relationship between these two variables, and the direction for that matter. That is, if you had the scatter plot that had a positive direction and relatively strong strength, like between these two variables, the weight in kilograms and the waist circumference, that number would be positive and large. Large for strong and positive for obviously positive direction. As opposed to the temperature and heating sales, that number would be negative because of the negative direction, and small because the small or weak association. This is exactly what correlation coefficient is. Correlation coefficient is the number that tells you the strength and the direction of the linear relationship between two quantitative variables. Now, that number is always between -1 and 1, and we usually write it with a lowercase r. And I have underlined here, and I should put asterisk on it, that it is the strength and direction of the linear relationship between these two variables. We have to determine whether the relationship is linear first. If it is not linear, this correlation coefficient often won't tell you the strength and direction, but could get them wrong. So let's talk about some examples of how this works, and then I'll show you some examples of when it doesn't work. So here are 6 scatter plots, and they are all positive directions with varying degrees of strength. On the upper left is very weak, as you can see the dots are very loosely scattered, and the bottom right is about as strong as you could get at almost a perfect line. And I have the correlation coefficients R written beneath them. So you can see when they're very loosely scattered up and to the left, the correlation coefficient is about 0, and perfectly strong, as strong as you can be, would be 1. And so anything in between there would be varying degrees of strong or weak. Closer to 1 is strong, closer to 0 is weak. And all of the numbers are positive because the directions are positive. And then there's a similar story with these 6 scatter plots. The weakest one is up and to the left, so the correlation coefficient is closest to 0, but the one in the bottom right, which is the strongest one here, has a correlation coefficient closest to -1. And then all of them in between there are varying degrees of strength. So closer to -1 is strong, and closer to 0 is weak. The only difference is now they're negative because the direction is negative. So here's a little table that will break down some examples of language you can use to describe correlation coefficients and little snapshots of a scatter plot of what it could look like. Here on the left-hand side are all the positive scenarios. So at the top we have correlation of 1, perfectly strong. Next, 0.8 to 0.99, very strong, 0.6 to 0.8, strong. Then it goes down to 0.2, 0.4 weak, and 0 to 0.2, very weak. And then on the right-hand side are the analogous graphs and correlation coefficients for negative ones. So if you're finding it hard to describe these and you're looking for language, remember sometimes less is more. And so here's some words you can use. Very strong, strong, moderate, weak, very weak. Those are perfectly fine. You don't need anything more than that when describing the strength. Now, a number like this doesn't just come out of the ether. It's something that you can calculate directly from the data itself. Here are 3 formulas to calculate the correlation coefficient. They are all algebraically equivalent. That is, you look at the same exact number no matter which one of these equations you use, and some of them are easier or harder depending on the format of the data that you have. Although we'll use technology a lot, your calculator and Jump will both do all of these for you if you'd like, but it's really nice to be able to pull this out by hand and understand where correlation coefficient comes from. So I'm going to show you an example of how to do this by hand using the very last formula. Now what I have here are the first 11 rows of the YouTube and sales data, and I've got my formula on the right hand side to calculate the correlation coefficient for these 11 rows. I'm going to calculate these in a table to keep myself organized. That way you can kind of see where everything is working together. So to work this formula, I'm going to have to add up, that is what the sigma, the big capital E looking thing means, the multiplication of the z-scores between x and y. And then I'll divide by how many I have, n minus 1. So I have set up my table to calculate z-scores for x, z-scores for y, and the multiplication between the two. So as soon as I fill all this out, all I'll have to do is do some addition and some division. So I'll start with YouTube, since that is x. So I will need to calculate the z-scores for all of those 11 observations using the mean for YouTube, which is 170.96, and the standard deviation for YouTube, which is 98.45. And I've put those z-scores in the column where it says z-score x. So the very first one, 0.7, that's the z-score for 239.76. The next one, negative 0.93, is the z-score for 79.32. And I rinse and repeat for the others. So after this, you can imagine calculating z-scores is going to be a breeze, since you'll get plenty of practice. Next, I need the z-scores for y, which is sales in this case. So I'll need to use these 11 observations along with the mean for sales, which is 17.42, and the standard deviation for sales, which is 6.62. So here are my z-scores for y. The very first one, negative 0.71, that is the z-score for 12.72. The next z-score, negative 1.07, is the z-score for 10.32, and then rinse and repeat for the rest. So all in all, I've got 22 z-scores here. So if you want practice calculating z-scores, it's one surefire way to do it. To finish this formula, I need to multiply those z-scores next, side by side. That's what zx times zy means. So for row 1, I'm going to take 0.7 and multiply it by negative 0.71. In the next row, I'm going to take negative 0.93, multiply it by negative 1.07, and do that for every row. So here are my resulting multiplications. Now keep in mind, I round to 2 decimal places here to keep the table nice and neat. So yours might be a little off, but if you round to 2 decimal places, you should get what I get here. Now my formula says I have to add all those up. Add up the multiplications of those z-scores. So I will add up that column. I get 8.25. And then the last thing I need to do in my formula is divide by how many I have minus 1. I have 11, so I'll divide by 11 minus 1, or 10. And that will give me my final answer of 0.825. So my correlation coefficient for YouTube and sales for the first 11 rows is 0.825. So 2 takeaways is the direction is positive because the physical number is positive, and it's closer to 1 than it is 0, so it is relatively strong. And I don't have to say anything more than that, just saying it's strong is plenty enough. Okay, so now before we get into using correlation, some words to the wise. I said that this only works for linear relationships, and I don't mean that you can't calculate this for other variables that aren't linear. What I mean is that if you do, it won't tell you what you think it'll tell you. And let me show you some examples of why. Here are 3 scatter plots. Now, these 3 scatter plots have very, very strong relationships. The one on the left is almost a perfect parabola that has a downward direction. The one in the middle is almost a perfect circle. And the one on the right is almost a perfect sine curve. So they're very strong relationships. They're just not linear. But if you were to take the data points in those plots, those scatter plots, and calculate their correlation coefficients, you would get correlation coefficients about 0. So if you weren't looking at the scatter plots and you just had this data in a spreadsheet, and you said, wow, look at these correlation coefficients. One is negative 0.03. One is exactly 0. One is negative 0.02. There must be no relationships here. You'd be wrong. It's just that the relationships aren't linear. And without looking at the graph, you wouldn't know that. So warning number 1 is that this only works for linear relationships. So before you go about calculating correlation coefficients, it's important to look at the scatter plot first. The next warning is that when we say correlation, we don't imply causation. That is, it's totally possible for 2 variables to be correlated. That is, you look on the graph and they trend upwards or downwards together, but that doesn't mean one causes the other. 2 variables can be correlated and they might not be causally related at all. So when we go to describe these variables that we're going to be working with, I want to make sure, and you want to make sure, that you're avoiding any language that might indicate causation. So stick to words like correlated or correlation or associated, not caused or leads to or anything that might indicate that kind of language. Some examples of why you might not want to use that causation language. are things called spurious correlations, or graphs with two variables that have a clear correlation between the two, but clearly have no causation between the two. Like these, the divorce rate in Maine and the per capita consumption of margarine. I think we can probably all agree that the divorce rate in Maine is not driving how much butter couples eat or don't eat. But if you just look at these two variables on the graph, you wouldn't know that. You'd say, wow, the strength seems pretty strong, the direction is negative, seems to be very highly correlated. But if you said they caused each other, you wouldn't be telling the truth. You wouldn't be accurately describing these two variables. Or this example, the total revenue generated by arcades and the computer science doctorate awarded in the US. Positive direction seems like a pretty straight line, very highly correlated, but one is clearly not causing one another. Just because you put two variables on a graph together doesn't mean one is going to cause the other. All we can tell from the graph, the scatter plot, is whether they are correlated. Correlation and causation are two very different things. Right. Getting back to our example, let's calculate the correlation coefficient for all of the observations for the YouTube and the sales data. So I'm going to pull it in a jump, we'll do it in jump, and go from there. So now that I got the YouTube and sales data in jump, I go to analyze and fit y by x. I put sales under y since sales on the y-axis for us, and the YouTube advertising on x since it's on the x-axis for us. Then I'll click OK, and it should give us our scatter plot, and I'll have to click the little red triangle to give it our summary statistics, which will include the means and standard deviations, and the correlation coefficient, which we're looking for. And here we go. So it says that our correlation coefficient is 0.78. And here are those summary statistics. And if you look in there, it says that our correlation is 0.7822. Now, if you remember, that is not the correlation coefficient we calculated by hand. That's because I only used the first 11 rows, not all of the observations. So not too bad. And if you wanted to describe that, you would describe it as strong. And honestly, very strong or strong, either one of those would be fine. And you'd also want to make sure you describe it as positive, strength and direction both. So up until now, we've got our YouTube and sales scatter plot, and describing it in form, direction, and strength. We would say it is mostly linear, maybe not perfectly, but it's pretty linear. The direction is absolutely positive, and the strength is strong or very strong. Strong is just fine. So that's all we're going to need for correlation coefficient. So I want to move into regression and how correlation coefficient plays into that. But to do that, we're going to have to recall something that you've probably seen before and or have done before, and that is y equals mx plus b. Now, if you're really well versed in y equals mx plus b, great. If you've never seen it before in your life, that's also okay. We're going to do a quick crash course on what it is and how we're going to use it. Y equals mx plus b is the equation of a straight line on an xy coordinate plane. So here on the right, I've got x and y axes, and I have a straight line. You could describe that straight line with an equation, and the equation always has the form y is equal to mx plus b, where m and b are particular numbers for the particular line you've drawn. M stands for the slope, that is how steep or flat a line that you've drawn is. Another way to describe slope is the change in y over the change in x, that is how much rise is there per unit change on the x-axis. So in this particular line, you have to go over 3 units on the x-axis before you get a rise of 1 unit in the y-axis. So we would describe the slope here as 1 over 3. B stands for the number where the line crosses the y-axis. Now, the line crosses the y-axis at a point which has 2 coordinates, x and y. So here it would cross at 0, 2. B is the second coordinate, the y coordinate, 2. So we can write the equation of this line as y is equal to 1 over 3 times x plus 2, where 1 over 3 is m and 2 is b. Now, other than describing the equation of a straight line in x and y coordinate plane, you can also plug in values for x and do some basic arithmetic and get values for y out. That is, when x is equal to 6, you can plug in 6, and multiplying by 1 over 3 gives you 2, and 2 plus 2 gives you 4. So you say when x is 6, y is equal to 4 in this equation. And since we use that equation, what that also means is that the coordinates 6, 4 is a point that lies on the line when you go over to the x and y coordinate plane. So any point that you pick on the line, its coordinates would work in this equation. If you plug in the x, you'll get the y out. And you might be wondering, why do we care about the equation of a straight line? Why do we care about y equals mx plus b? The reason is that this is what we're going to use to predict how many sales and units we can make based off of how much we spend on YouTube advertising. Because if we had an equation like this that described our data, then instead of x, we would just say the amount spent on YouTube advertising, and we would plug that amount into our equation, and what we got out for y would be the sales in units that we would expect to make. The only thing stopping us from doing that is that we don't have an equation like this for our data. We need to figure out what m and b would be for our data, then we can write this equation, then we can use it to make predictions for the sales in units. Now just a little terminology moving forward. Instead of x when it comes to regression, we usually call that the predictor, or the explanatory variable, or the independent variable. Unfortunately, you're going to hear all three of those terms, and I wish there was only one, but there's not. I will try to be consistent. I usually use independent variable, and so does your book. But just be aware moving forward in other courses, if they say predictor or explanatory variable or independent variable, they're all talking about the same thing, x. On the other hand, we usually call the variable y either the response variable or the dependent variable. Again, you're going to hear these terms used equally as much outside of this class, but in this class, I will try to be as consistent as possible and just use dependent variables. When I say dependent, I mean y. And if somebody else says response, they also mean y. So the idea here is that if we had such an equation for the YouTube and sales data, a y equals mx plus b equation, we could use it to answer the question of how many units we would expect to sell if we spent $200,000 in advertising. All we'd have to do is plug 200 into the equation. One, because it's in thousands of dollars, so we plug in 200, not 200,000. And whatever we got out for y would be the expected number of sales we would make. Now, a little more terminology before we go forward. That equation is called a regression equation. So we don't call it y equals mx plus b anymore, we call it a regression equation. And one of the ways that we use it is we use it to predict a value for y given a certain value of x. So we'll plug a certain x in and see what y comes out to be. Now for any particular certain value of x, there might already be a value for y in our data set. So what's in our data set for y and what we get out of the equation for y could be two very different things. So we're going to denote them this way. Here I've got a data point x and y in red. That is a physical data point in our data set. But if you plug that same x value into the equation, you'll get a point on the line. That's the one in green. So the green y and the red y are two different values, although they come from the same x. That particular observation, that red dot, is row number 4. You can see it in jump here on the right. That's when x, YouTube advertising, is 181, and y, sales, is 22. Now you notice that the green dot is also for 181. That's when x is 181. But y is not 22. Y, if you trace the green dot over to the left, is probably more around, if I had to eyeball it, 15 or 16. We'd have to plug 181 into the equation to see what the equation would give us. So because the y value for the equation and the y value in our data set, red and the green here, could be different, we can't call them both y. So that green value of y, that's the amount of sales associated with a particular x when you plug that x into our regression equation. So quite literally plugging 181 into this regression equation and seeing what the value for y is when you do the arithmetic. That green value of y is called a fitted value or a predicted value. Again, it's not the value of y in our data set for that particular x. It's the value of y you get when you use the regression equation. So when we write it, we won't write y, we'll write y with a little triangle on top. Sometimes you call that a hat, so you might hear this called y hat, but that is our fitted value or our predicted value for a particular x. Now, since we're going to have a lot of data points as well, we can't call every data point x and y, so we'll use subscript to denote which data point we are talking about. Here I've wrote subscript I just as a general placeholder, but if you had a particular data point like row number 1, you would write subscript 1s for both of these. Or if I wanted to show you what data point 17 looked like and what its prediction was, I'd write the subscript 17 on all of them, just like this. Now another little bit of notation. we don't write our regression equation as y equals mx plus b literally. We will write, instead of m, b1, instead of the slope b, b0. Nothing wrong with m and b by themselves, but eventually we're going to use more than one x. We're going to use more than one variable to predict y. And so every time we do that, we're going to have 1, 2, 3, 4, maybe 17 of these variables. So numbering them off is going to become a lot easier than just coming up with new letters. So we're using one x here, so we call that slope b1. If we had a second, we would call it b2, and so on and so forth. So I want to try and find such a regression equation for our data set, the YouTube and sales data. In other words, I need a slope b1 and an intercept b0 to form my regression equation. Y equals mx plus b, so to speak. The problem is, what equation should I use? What line should I draw through my data set? I mean, it kind of makes sense that you would want one that would follow the direction of the points and one that would fit the points well, a best line per se, but what do I mean by best? What do we mean by best? How will we determine if we have a good equation or a bad equation? So not that there's a single one way to determine what's best, but I'm going to walk you through one way. It's a very, very common way, and it's the way we're going to use, but there are others. And so this is how we are going to determine what is the best. Which equation should we be using? What line should we be drawing if we have a particular data set like we do here? So to tell how good a regression equation is, we're going to start by choosing one particular x, say 181. Then I'm going to go into my data set to see what the value for y is for that x, and say it was 20. Then I'm going to plug 181 into my regression equation to predict what y would be. And then let's say I get 16 when I do that. So I've got two values for y. I've got the predicted one using my regression equation, 16, and I have the actual one for my data set, 20. Both is for when x is 181. Now the difference between those two numbers, 20 and 16, is 4 if you do the subtraction in this order. The actual value, 20, and the predicted value, 16. And remember, this is thousands of units. So when spending on YouTube advertising is $181,000, our prediction is off by 4,000 units. So is that a lot? Not a lot? It's contextual, but for when X is $181,000, our prediction is 16,000 units. And based off of our actual data set, that is off by 4,000 units. That difference is called a residual. And for some data points, it'll be smaller than that. And for some data points, it'll be larger than that. It depends how close that observation, that data point, that dot on the scatter plot is to the line, our regression equation. So to tell how good your regression equation is doing, you would do this for every data point, not just one. So I've done 6 here. The residuals are 1, 3, -3, +2, +1, -4. The positive residuals are for points above the line. The negative residuals are for points below the line. So you might think, yeah, well, let's add these up, and that'll tell us how good we're doing all together. But the problem is that the negatives and positives very well could cancel out, and these 6 particularly will cancel out to 0. Now, are these all points 0 away from the line? No, it's just that the positive negatives canceled out. So similarly, for when we're dealing with variance and standard deviation, to stop these from canceling out, we're going to make them positive. But to make life easier for us moving down the road and thinking ahead, instead of just taking the absolute value, we're going to square all of these. So squaring all of these residuals and adding them up, I would get 40, at least these 6. And that number tells me how far off I am altogether. The bigger the number, the further away my points are together. The smaller the number, the closer they are to the line. And 0 would be perfect. 0 would mean they are all on the line. All of my predictions are exactly the data points themselves. Now, is 40 itself good or bad? This is a relative measure, so we would use this to gauge whether it's better or worse than other regression equations. So given another regression equation, which one has the smaller number? And that's the one we would pick. This value is called the sum of squares or sum of squared residuals. When this is big, that means the points are far from the line. When it's small, that means the points are close to the line, 0 being the best. Now you can think about this as the sum of squared numbers, because that's literally what we have been doing. Or you can think about them as the area of literal squares. So if you had a square where the sides was 3 and 3, the area is 9, and that would be the squared residual for that case. To show you an example of how this works, I've loaded up an applet in GeoGebra. GeoGebra is a free online tool that you can use to make math and stat interactive applets. And this one particularly will let you calculate the sum of squares for these 4 data points if you draw an equation, if you draw a straight line, and it'll calculate that for you. So I'm going to draw a few and see what our sum of squares ends up being. So there is my first line. It's in green here, and it says the sum of squared residuals is 26.92. And you can see it's actually mapped out the squares. That's the distance from the line, and you square the numbers, so you have these literally squares, and the area of those squares together is 26.92. Is that good, bad? This is relative, right? So I'm going to draw another line to see if I can do better. And better would be something smaller than 26.92, where 0 would be the best. Now the second line I've drawn is a little bit flatter, but you can see the sum of squares is larger now. It's 40, so I haven't done better, I've done worse. So I'm going to draw a third line to see if I can do any better yet. So this third line, I've canted it even further downward, and the sum of squares is not smaller again, it's larger yet, it's 73. So I'm not moving in a good direction. I need to keep drawing lines until I can make this smaller. Now, as I do this, I'm keeping in mind that the best here is going to have the smallest possible sum of squared residuals. Since these data points are not going to lie on a straight line, I can't hope for 0. 0 is often impossible. So the best I can hope for is to make this as smallest as possible. Now, I don't know what smallest is going to be in this case, but there is one that would make it the smallest. There is an equation that'll do that, and that's my goal. This method is called ordinary least squares. Least squares meaning we are trying to find the smallest sum of squared residuals. And it's called ordinary because it is the very first method of its kind when it first came about. Since then, there have been many other adaptations to take into account different forms of data, weighting different data points differently, but this was the original method that used this type of distance from the line, and that being used to determine what is best. So when we find this best line, we call it the line of best fit, or the least squares line. And it'll have a particular slope, b1, and a particular intercept, b0. Now, instead of sitting here drawing lines all day long and hoping that we make a good guess, you can actually use basic calculus to derive direct formulas to calculate what the best slope and best intercept would be to give you this line of best fit. So we don't have to guess and check. There are formulas that'll give you b1 and b0 straight away, and the formulas use the information from our data directly. The formula for the best slope, b1, is the correlation coefficient between x and y times the standard deviation of y divided by the standard deviation of x. b1 is the slope of our line. It determines whether the line is very steep or very flat. Now, if you think about the numbers that go into this, it's determined by the correlation coefficient, the strength, and the direction of the relationship between x and y. So the strength and direction will determine the slope of the line, which kind of makes intuitive sense. And what also plays into here is the spread of x and the spread of y measured by standard deviation. So to find the best b0, the best y-intercept, that'll be determined by the mean of y minus b1 that we found before times the mean of x. That is, the best slope and the best intercept are determined by basic summary statistics about x and y, the mean of both of the variables, the standard deviation of both the variables, and the correlation coefficient between the two. Now, with these two equations, calculating the line of best fit is not all that complicated anymore. It's two equations, some basic math operations, addition, subtraction, division, multiplication, and you've got yourself a line of best fit. But just because you have a line of best fit doesn't mean it is a good fit. So I have two scatter plots here, one on the left, one on the right, and you can see there's a red line going through each of them. Each of these red lines is a line of best fit. That is, you cannot do any better than those red lines. With that said, I think one of these lines is doing a much better job of describing its scatter plot than the other. And I would argue it's the one on the right, the one where the data points are much closer to the line than the one on the left. And it's not that the one on the left isn't the best line for that case. It is. That is the best fit line. You can't do better. But is it a good line? I think that's up for debate. So we still need to decide what's good. We've decided what is best, but what is good? Now, to determine what is good, I usually use a music analogy. Like, if you've ever played music, there's the notes on the page called sheet music. And if you're playing notes, it's good that you hit all of the notes. And if you miss a note, you can be off by a little bit. So you can be a little bit under, a little bit above, or you can be off by a lot, really above or really below. And basically what's happening here is that is our regression equation. Our regression equation is getting close to our data points, and we want it to be as close as possible. And how far off it is from each data point, like missing a note, is the residual. And so we're going to measure how far off all the notes are from what we're playing, and big is bad and small is good. That was our sum of squared residuals. So we're going to use that value to determine what is good and what is bad, not just what's best. We're going to use what's called the percent of variation in y being accounted for by the regression. We're going to calculate how much variation there is in our y variable. So in notes on a page, how many ups and downs are there? Are there a lot? Are there not that many? Then we're going to see how many of those ups and downs, percentage-wise, is our regression equation accounting for. That is, if you were playing the notes, how much of the ups and the downs are you accounting for? And if you're missing, how far are you missing? A lot or not a lot? Now, this isn't something that we're going to calculate by hand, but it's something good to know where this comes from. So the total variation in y can be calculated by taking each value for y minus the mean and squaring it and adding it all up. So that's how many ups and downs there are in the data set for the y variable. To find out how much of that variation we are missing, we can utilize our residuals. Our residuals are how far are the y values from our predicted ones. So we will take that difference, square them, gets our residuals, and we're going to add those up. So we've got these two numbers, how much variation there is in y, and how much of the variation are we missing. The sum of squared residuals and the sum of squares for y. So if you wanted to know the percent of variation that you are missing, you would just take the ratio of those two numbers. The sum of square root of the y on the bottom, how much total variation there is, and the sum of squared residuals on top, how much of that variation are we missing. So if you wanted to know the percent of the variation you are accounting for by using this regression, it would simply just be 1 minus that number. 1 minus the sum of squared residuals divided by the sum of squares in y. And the idea here is that percent is really good when it's high. We want to explain a lot of the variation in y by using our regression. And since it's a percent, 100 is the best and 0 is the worst. So higher the better, lower the worse. Now, in our particular case, when we have one x and one y, there is a mathematical shortcut for calculating this percentage of variation that we are accounting for by the regression. And it's simply taking the correlation coefficient r and squaring it, which leads to why we call this value r squared commonly. So we won't use the phrase percent of variation in y accounted for by the regression. What a mouthful. We'll just say simply r squared. So when r squared is closer to 1, that's better. When r squared is closer to 0, that's not so good, that's worse. Just to give you some context, very rigorous scientific experiments often can achieve r squareds in the range of 80 to 90%. So in terms of playing music, the ups and the downs, not only are they hitting the notes, but they're not very far off. Observational studies, on the other hand, oftentimes can only hit a range of 30 to 50%. So not only are not hitting a lot of notes, but when they don't hit them, they're missing by a lot. All right, so it's time to tie all this together. I think we have enough to answer our first two questions. So we need the correlation coefficient for our YouTube advertising and sales. We will use that in basic summary statistics to calculate the line of best fit, and then we'll answer those two questions we started with. Now, luckily before, we'd already calculated the correlation coefficient. We found it to be 0.7822. That is positive and strong or very strong. Either one of those is just fine. So to do the line of best fit, we'll need some summary statistics. So I've got some basic summary statistics here on the left and the right. Should have everything we need plus some. And we've got the equations here in the middle for the best slope and the best intercept. So let's walk through calculating these and we'll put them together to make our equation. Now for the best slope, we need the correlation coefficient and the standard deviation for both x and y. And so I have red boxed here all the numbers that we're going to be needing for this entire process. So there's a lot of extra stuff here. So I'm going to pull that correlation coefficient and the two standard deviations and put them in their appropriate spots, remembering that x and y have to go in the appropriate spot. Standard deviation for y needs to go on top, and the standard deviation of x needs to go on the bottom for the slope. That is, my best slope should be 0.78 if you round to 2 decimal places, times 0.626 divided by 103.03, which would give you 0.047, and that is the best slope for our line of best fit. So that will be B1 in our equation. For the best intercept, B0, I'm going to need the mean of both of the variables and B1 that I just calculated. So I'm going to put them in their respective spots, remembering that y and x have to be put in appropriately, not swapped. Very easy mistake to make. The mean of y is 16.83, that is sales, at minus B1 0.047 times the mean of x, 176.45, and that is for YouTube advertising. So as a best B0, the best y-intercept, I get 8.54. So forming my line of best fit, I have y is equal to my slope, 0.047 times x, plus my intercept, 8.54. Now I have calculated this using jump, and you can see that our intercept and our slope are actually very similar to what they found. I did some rounding, so a little bit off is to be expected, but man, pretty dang close even for rounding. And so this is the equation that we can use to predict sales based off of how much we spend on advertising. Now, sometimes you'll be hearing this called a model, and the reason is simply because we use it to model sales based off of advertising. But you can call it regression equation, that's just fine. So let's move on to answering those two initial questions we started with. Well, our first question was, do we think it's worth spending more advertising in terms of sales? And the correlation coefficient seemed to be very positive, very strong. So I think, yes, it seems to be worth it. But the second question, how much could you expect to sell if we spent $200,000 on advertising? We're going to utilize our regression equation. So we're going to take 200, plug it into our equation, and see what y comes out to be. Now note, I'm not using 200,000, I'm using 200. The reason being the units are in the thousands. So you need to keep the units straight or the answers aren't going to make as much sense. So plugging in 200, I get 17.94 for y. That is, I would predict that we would sell 17,940 units. And remember, that is also in thousands of units. And remember, I'm using also correlation, not causation language. So I'm not saying this is what's going to happen. I'm saying this is what we would expect to happen. This is what is associated with $200,000 in advertising according to our regression equation. Now we can go one step further and ask ourselves, well, how good is this regression equation? It's the best, but how good is it? What percent of variation in sales is being accounted for by our regression equation that uses YouTube advertising? So that value is called R squared, also called the coefficient of determination. And all we have to do to calculate that is taking the correlation coefficient and squaring it. So our correlation coefficient was 0.7822, squaring it gives us 0.6118, so 61%. We are explaining 61% of the variation in Y by looking at YouTube advertising. If this was sheet music, we are 61% hitting the ups and the downs. Is that good? Bad? That is contextual, but from a scale of 0 to 100, that's the percent of variation we're accounting for. Now, why might not that be closer to 100? Well, what other things could be affecting how much we make in sales? Maybe not just advertising, right? Maybe it's a slew of other factors. So if we looked at other factors, maybe we get closer to 100, but if we just use YouTube advertising, we're getting 61%. Now, the last two things I want to cover are that the slope and the intercept, B1 and B0, are actually useful in and of themselves. They have useful interpretations past just predicting what Y could be. So how do we interpret what those numbers mean? And the answer is we're going to go right back to Y equals mx plus b. What does slope mean, and what does the Y-intercept mean? Generally speaking, the Y-intercept is the value for Y when X is 0. But in our context, X is the amount spent on YouTube advertising. So when we spend $0 on YouTube advertising, we would expect Y to be 8,540. That's the value for Y in our context. 8.54 in thousands of units is 8,540, and that's units sold. So we would say we would expect to sell 8,540 units if we spent $0 on advertising. What is Y when X is 0? The interpretation for B1, the slope, is when X increases by 1 unit, what is the change in Y? Does Y go up or down, and by how much? But in our case, an increase of 1 unit on X is an increase of $1,000 on spending on advertising, and the slope associated with that is 0.047, and in thousands of units, that's 47. So our interpretation is when X goes up by 1 unit, $1,000 in spending on YouTube advertising, Y goes up by 47 more units sold. So here are both of those interpretations. An easy way to remember how to do these is to write out the interpretation in terms of algebra. Slope, when X goes up by 1, Y goes up by the value of the slope. Intercept, when X is 0, what's the value for Y? And once you have that written down, substitute in the values for B1 and B0, and write in the words for X and Y. Instead of X, write advertising. Instead of Y, write sales. And there you have it, your interpretations for B1 and B0.